Right now, as I record this, the surface of Lake Mead is sitting at about 1,042 feet above sea level. On its own, that number means nothing, so let me give you the one that gives it teeth. The all-time record low for this reservoir, the lowest it has been since crews closed the gates and started filling it in the 1930s, is 1,041.71 feet. That was set on July 27th, 2022. As of this month, we are within inches of it, and the Bureau of Reclamation's own projections say we do not stay above it. Behind that surface, standing in the water upstream of Hoover Dam, are four concrete towers. Each one is 395 feet tall. Together, they contain 93,674 cubic yards of concrete and just over 15 million pounds of steel. They are the only way water gets from Lake Mead into the machinery of that dam. Every kilowatt-hour Hoover has ever produced came through those four towers, and there is a question that gets asked about them constantly, usually badly, usually with a photograph of a bathtub ring attached. What happens if the lake drops far enough that the intake towers reach air? I'm Simon. I'm a hydropower engineer. I want to be straight with you before we go any further, because the honest answer is not the one that makes headlines. The intake towers reaching air is not the first thing that goes wrong at Hoover Dam. It is very close to the last. There are several failure modes that arrive well before it, and every one of them is more immediate, more expensive, and far more likely than the image most people have in their heads. The towers are not the fragile part of this system. They may be the least fragile part of it. So this is not a video about a dam breaking. Hoover is not going to break. This is a video about what actually degrades first, in what order, and why the number everyone quotes is the wrong number to be watching. By the end of this, you will understand the four thresholds that matter, what physically happens at each one, and which of them the engineers running that dam are genuinely worried about in 2026. Let's start with the towers themselves, because you cannot understand the failure sequence without understanding how strange they are. Go back to 1931, Black Canyon, the Colorado River still running through it. Before anyone could pour a foot of the dam, the river had to be moved, and the way they moved it was to bore four tunnels through the canyon walls, two on each side, each one 50 feet in diameter. Combined length, 15,946 feet, just over 3 miles of tunnel excavated to 56 feet and then lined with 3 feet of concrete. On November 14th, 1932, the river went into the two Arizona tunnels and the canyon floor went dry. Those tunnels are the key to the whole design, because reclamation did not abandon them afterward. The two inner tunnels were plugged with concrete about a third of the way along, and then 30-foot diameter steel pipes were run through them. Those pipes connect the intake towers to the power plant. The outer tunnels were plugged near their midpoints, and their downstream halves became the spillway outlets. Nothing was wasted. The diversion works became the permanent works. Now the towers. 4 reinforced concrete structures, 2 on each canyon wall, each built on a rock bench cut into the wall itself, 82 feet in diameter at the base, tapering to 63 feet 3 inches at the top. Inside each one is a barrel 29 feet 8 inches across, surrounded by 12 radial buttresses. Those buttresses do two jobs. They stiffen the structure and they hold the trash racks, which are steel gratings that keep debris out of the water before it enters the penstocks. The trash racks alone weigh just over 7 million pounds. Here is the detail that matters most for everything that follows. Each tower does not have one opening. It has 2 sets, 12 openings at the base of the tower and 12 more roughly halfway up. Flow through them is controlled by 2 cylindrical gates, each 32 feet in diameter and 11 feet tall. One gate near the bottom, one near the middle. Total weight of the gates across all 4 towers, 5,892,000 pounds. Read that design again, because it is the answer to the question in the title. The engineers who built this in the 1930s did not put the intake at 1 elevation and hope. They put it at 2. They built the ability to draw water from high in the reservoir or low in it, depending on conditions. Whoever laid that out understood that a reservoir on the Colorado River would not sit at one level for the next century. From the towers, water travels down 30-foot penstocks and then splits into 16 13-foot penstocks that feed the turbines. 44,000 tons of steel were formed and welded into 14,800 feet of pipe for this system. The largest sections are 30 feet across, with walls 2 3/4 inches thick. A single 12-foot length of that pipe weighs enough that only 2 of the steel plates it was made from could travel on one railcar. Two lengths welded together make a section of about 135 tons. At the bottom of all of that sit 17 main turbines, 9 in the Arizona wing, 8 in the Nevada wing, Francis-type vertical units. They were replaced in an uprating program that ran from 1986 to 1993, and the plant carries a nameplate capacity of about 2,080 megawatts. In a good year, Hoover has produced over 10 billion kilowatt hours. Its record was 10,348 million in 1984. Its worst year since 1940 was 2,648 million in 1956. Hold on to that gap between the best year and the worst year. It tells you this plant's output has always moved with the river. What is happening now is different in kind, not just degree, and I will show you why. To see it, you need one concept, and it is the concept the entire story turns on: head. Head is the vertical distance the water falls between the reservoir surface and the turbine. That is where hydroelectric power comes from, not from water moving, from water falling. Drop the reservoir surface and you have not just taken away water. You have taken away the height that water falls through, and the power available falls with it. Reclamation publishes Hoover's operating range directly: maximum head, 590 feet, minimum head, 304 feet. Average 510 to 530 feet. Notice something about that range? The minimum is roughly half the maximum. Cut the head in half and you do not lose a little power. You lose most of it because output scales with head and with flow together, and both of them shrink as the lake drops. Full pool at Lake Mead is elevation 1,229 feet. As of mid-July 2026, the lake is at about 1,042. That is roughly 187 feet below full, and the reservoir is holding about 27% of its capacity. So the first threshold has already been crossed years ago, and it was never a dramatic one. There was no alarm, no evacuation, no cracked concrete. Hoover simply became a weaker version of itself, gradually, over 2 decades, with almost nobody watching the number. Now the second threshold, and this is the one I want you to remember instead of deadpool. Elevation 1,035 feet. That number has nothing to do with air reaching the intakes. The towers are nowhere near exposed at 1,035. That number is about the turbines. A Francis turbine is designed around a specific head and a specific flow. Run it near that design point, and it is one of the most efficient machines humans have ever built. Run it far below that design point, and the water stops arriving at the runner blades at the angle they were shaped for. The flow separates, pressure fluctuates. The machine starts to vibrate in ways it was never meant to. Below its design range, a Francis turbine can develop what engineers call a draft tube vortex rope. Downstream of the runner, in the widening passage that carries water away, the residual swirl in the flow organizes itself into a rotating corkscrew of low-pressure water. That rope processes around the passage, and it drives pressure pulsations through the whole water column. Those pulsations shake the machine. Sustained, they cause fatigue in the runner and the shaft, and they can drive cavitation on the blades, which is water locally dropping below its vapor pressure, flashing into vapor, and then collapsing back into liquid against a steel surface with enough force to pit it. This is why the reporting on Hoover's older units is what it is. Those units face serious damage risk below elevation 1,035 feet. Not because there is no water, because the water arrives with the wrong energy and the machine punishes itself trying to use it. And the capacity numbers reflect that. Below that elevation, Hoover's generating capacity has been reported as dropping from roughly 1,302 megawatts to about 382. That is roughly a 70% reduction, and it does not come from the reservoir running empty. It comes from having to shut machines off to protect them. Now put that against the forecast. Reclamation's 24-month study, in the most probable case, has Lake Mead reaching about 1,036 feet by October of this year, roughly 4.5 feet below the 2022 record. Projections extending further show the lake around 1,020 feet by July of 2027, and under the probable minimum scenario, below 1,000 feet by June of 2028. That is the threshold that is arriving. Not deadpool, not air in the intakes, a turbine efficiency and equipment protection threshold, roughly a foot below where the lake sits as I record this. And the response to it is already underway, which tells you how seriously the agency takes it. On May 21st of this year, federal officials announced approximately $52 million going into infrastructure, operations, and maintenance at Hoover Dam. Part of that is the purchase and replacement of up to 3 of the older units with what are called wide-head turbines. A wide-head runner is shaped to hold acceptable efficiency across a much broader range of head rather than peaking sharply at one design point. Reported estimates put them at $8 to $13 million per turbine. They are expected to restore at least 160 megawatts of capacity, and construction is not expected to wrap until October 2028 at the earliest. Sit with that timeline for a second. The lake is projected to cross the damaging threshold this October. The equipment designed to operate below that threshold is not expected to be finished for another 2 years after that. That gap is the actual engineering problem at Hoover Dam in 2026, not a wall of water, a calendar. Now let's go to the question in the title, because we have finally earned it. What happens when the water surface actually approaches an intake opening? The concept you need is submergence. Submergence is simply the depth of water above an intake. It sounds trivial. It is not, because there is a threshold called critical submergence, and below it, the behavior of the water changes completely. You have seen this in a bathtub. Full tub, pull the plug, and the water just goes down the drain. Let the tub drain most of the way, and at some point a spinning funnel forms above the drain, and you hear it start to pull air. Nothing about the drain changed, only the depth above it did. Scale that up. When submergence over an intake drops below critical, a free surface vortex forms. At first it is a surface dimple, then it deepens, then it becomes what the literature calls an air core vortex, a rotating column of air reaching from the surface down into the intake. And once that happens, the intake is no longer drawing water. It is drawing a mixture of water and air. That mixture is the problem. Research on hydropower intakes is consistent on what entrained air does. It reduces the discharge through the intake, so you lose flow you were counting on. It degrades turbine performance. It causes vibration in the machinery. And in a long pressurized waterway like Hoover's penstocks, it raises the risk of transient events, pressure surges traveling through a pipe that was designed to carry solid water, not a compressible mixture. This is also why operators of hydro plants everywhere deliberately maintain a minimum submergence above their intakes, and it costs them real money. That water below the minimum is water they own and cannot use. It sits in the reservoir as unusable storage, purely to keep air out of the machine. So could a free surface vortex form at Hoover? In principle, at sufficiently low submergence over a given opening, yes, that is physics, not speculation. But look back at the geometry. 12 openings at the base of each tower, 12 more midway up, and 2 independent cylinder gates to select between them. The operators are not stuck with a single intake elevation waiting for the lake to fall past it. They can close the upper gates and draw from the lower openings, keeping the working intake deeply submerged long after the upper set would have been in trouble. That is not a modern retrofit. That is 1930s design intent, and it is the reason the honest answer to this video's title is less dramatic than the question implies. Hoover's intakes reaching air is not a scenario that sneaks up on an operator in a single bad summer. It is a scenario at the very bottom of the reservoir, well past the point where the plant has already been derated, and well past the point where much larger decisions have been made. Which brings us to the last 2 numbers. Elevation 950 feet is generally described as minimum power pool, the level below which generation is no longer considered viable. The wide-head turbines now being purchased are specified to operate down toward that elevation, which is exactly the point of buying them. Elevation 895 feet is deadpool. And I want to be precise here because this term gets used loosely all the time, including by people who should know better. Deadpool is not the level where the dam stops making electricity. That is minimum power pool, and it is 55 feet higher. Deadpool is the level below which water can no longer pass through Hoover Dam downstream at all, not less water, none through the normal works. The gap between those two, from 950 down to 895, is the band people are describing when they picture exposed intakes, and even there, precision matters. The towers are 395 feet tall, standing on benches cut into the canyon walls. Talking about them as if they were a straw in a glass understates what is actually a graduated system of openings and gates. As of mid-July 2026, the lake is roughly 90 feet above minimum power pool and roughly 147 feet above deadpool. Now, none of that means the situation is fine. It means the danger is arriving in a different form than the popular one, and I would rather you understand the real one, because here is the part that already happened, to a different set of intakes, and almost nobody outside Nevada noticed. Las Vegas draws roughly 90% of its drinking water from Lake Mead through intakes in the reservoir. In April of 2022, the Southern Nevada Water Authority released photographs of the top of intake number 1 standing above the water surface. Not projected, not modeled. Photographed. That intake sat at approximately 1,050 feet. And the reason that was a news photograph instead of an emergency is that Southern Nevada had spent more than $1.3 billion building the thing that made it survivable. A deeper intake, informally called the third straw, drawing at roughly 860 feet, paired with a low lake level pumping station capable of moving water even when the reservoir surface falls below where gravity alone will carry it. That system was operational when the upper intake came out of the water. I want to be careful about the comparison because these are different structures serving different purposes. Hoover's intake towers and a municipal water intake are not the same thing, but the lesson transfers exactly, and it is the reason I wanted to make this episode now rather than later. Southern Nevada did not wait for the emergency. They built the redundancy while the problem was still a projection on a chart, and they spent over $1 billion doing it. And they took criticism for the cost at the time. Then the lake fell. The upper intake came out of the water, and it was a photograph instead of a crisis. That is the whole lesson of this profession, and it is why I keep coming back to it. You build the boring redundancy before you need it. You spend the money while the problem is still theoretical, because the window to act closes long before the consequence arrives. Now hold that beside Hoover's timeline. The wide-head turbines are the right answer. The engineering is sound, the funding is real, and the specification correctly targets operation below 1,035 feet. But construction is not expected to be complete before October 2028, and the projections put the lake below that elevation this October. That is not a failure of engineering. It is a failure of lead time, and lead time is the one thing you cannot buy back once you have spent it. I want to be honest about the limits of what I can tell you, because that matters more than sounding certain. I do not know where Lake Mead will be in October. Nobody does. These are projections from Reclamation's 24-month studies. They are published as ranges rather than predictions, and they move with every snowpack season on the upper Colorado. Anyone giving you a confident date is telling you more than the data supports. What I can tell you is the direction, and the direction has been consistent for more than 20 years. And I will not tell you this dam is in danger of failing, because it is not, and the record does not support that claim. Hoover is a concrete arch gravity structure carrying its load into the canyon walls, and the loads on it decrease as the reservoir drops. A falling lake is not a structural threat to that dam. If anything, structurally, it is the opposite. What is at risk is capability, the ability to generate, the ability to deliver water downstream at the volumes an entire region has planned around. Hoover has averaged roughly 4.2 billion kilowatt hours a year, power that flows to Nevada, Arizona, and California under allocations set decades ago. That is the thing being quietly subtracted, a foot at a time, without anything visibly breaking, which is what makes this different from most stories in this field. There is no morning where a siren goes off. There is no crest collapsing at 11:55. There is only a number on a gauge that goes down more years than it goes up, and a set of thresholds that get crossed one at a time while the structure itself sits there looking exactly as monumental as it did in 1936. So let me answer the question I opened with, plainly. If the intake towers at Hoover Dam ever reach air, that will not be the story. That will be the epilogue. By the time water is low enough to pull a vortex into those openings, the plant will have been derated for years. The older turbines will long since have been shut down to protect them. Minimum power pool will be in the rearview mirror, and decisions far larger than any engineering fix will already have been made about who gets water on the lower Colorado. The towers are not the vulnerability. They were built by people who assumed the lake would move and gave themselves two sets of openings and two gates to move with it. Almost a century later, that assumption is the most forward-looking thing about the entire structure. The vulnerability is 35 feet higher in the machinery, on a schedule that does not line up with the reservoir. That is the number to watch. 1035. Thank you for spending this time with me. If you work at Hoover, at Reclamation, or anywhere on the Lower Colorado system, I would genuinely like to hear from you, and corrections are always welcome in the comments. Every figure in this episode was checked against primary Bureau of Reclamation documentation and published reporting. And where something is a projection rather than a measurement, I have tried to say so out loud. I'm Simon. Watch the water and watch the number nobody is quoting. I'll see you next time.